So we got past this point, but we did talk about sets and what a set is. And we listed off our positive even numbers, yes? And the first number we put was, remember, because it should be on the first page. Because we said the first positive even number is 0, then we said 2, 4, 6, 8, 10, ... Yes? There's a reason I'm coming back to this, because literally the next hour, my brain caught up with me. 0 would not be included. 0 is an even number. It is not positive. 0 is even, but it can't be positive or negative. So we can't include it in this set because it specifically states positive even numbers. If it stated non-negative numbers, 0 would be included because we're saying numbers that aren't negative. Well, 0 is not negative, so it would be included. So when we talk about numbers non-negative, we're talking about 0 and bigger. So I just wanted to go back and restate that. It's a small technicality. We really didn't necessarily have to talk about it, but 0 wouldn't be included. You good?
Yeah, I changed my classes.
Okay.
So the thing is over here.
Okay.
It's okay with the second.
Yep. You're good. So what we did, we're finishing up the note sheet from yesterday.
Yeah.
You probably noticed it, but yesterday when we were talking about this here, the set of positive even numbers, how we started with 0. That's not true. Because 0 cannot be positive or negative. So we have to remove it. If that makes sense. Yeah, so right there on that first page. Yeah. Yeah. Spaced yesterday. Wasn't thinking straight, so it's just 2, 4, 6, 8, 10 going on. Then we talked about our number types. We did these here. We talked about subsets, and I believe we finished all of our subsets, and we are right here on bounded and unbounded intervals. So we're going to be talking about interval notation, and equalities for the next little bit. Now there's two main types of intervals. There's bounded and unbounded. There's going to be 2 endpoints, or 1 endpoint, and it continues on indefinitely in one direction or the other. Now let's look at this here. The bounded intervals. Let A and B be 2 real numbers such that A is less than B. All that's saying is this. We have 2 points. We have 2 numbers. One of them is smaller than the other. That's all that first line is saying. A is less than B. So if A was, say, 14, B has got to be 15, 16, 17, something bigger than it. That's all that first line says. Then A and B are the endpoints of 4 different bounded intervals on the real number line. Now the first example or setup that we have is that A is less than or equal to X is less than or equal to B. That's our inequality of this. The interval, we have bracket A comma bracket B. Our brackets signify that that point, that endpoint is included, it's filled in. Our next one that we have is A is less than X is less than B. This here, the endpoints aren't included, so especially in interval notation, we use parentheses instead of brackets. And on the number line, A and B, those 2 endpoints are open circles. Last two are similar. The first one, we're saying that point A is included and B is not. And in the last one, we're saying that B is included and A is not. So we can either have a line segment, a bounded interval where both endpoints are closed, both are open, or one is closed and one is open. Those are the three, or really the four types of bounded intervals that we can have. Questions on bounded intervals? Let's look at the other type. We have unbounded intervals. Let A be a real number. Each of the real number lines shown below is called unbounded. So unbounded has one endpoint and continues in one direction or the other. It's going off in one direction. Now this here, again, we have four main types that we could have, really possibly five. And then we have that x is greater than or equal to a. So everything bigger than whatever the value of a is, and it's included. So bracket a comma infinity. Our second one, x is greater than a. So this time we're not including a. So we have parentheses a comma infinity parentheses. Our third one, x is less than or equal to a. So we're saying all the values less than or equal to that amount. So we're going to the left. So we'd have negative infinity comma a. And then the last one, x is less than a, so it is going to negative infinity. And at a, we're not including it, so it would be a parentheses. So we use brackets to show that it's included, parentheses to show it's not. We don't include that point. And interestingly enough, with infinity, infinity is always going to have a parenthesis. We will never put a bracket with parentheses. And part of the reason for that is because we can never get to infinity. Infinity is more of a concept, not an actual number. Like any other number that we can write, infinity is more of a concept. Because no matter what we do or how hard we try, we can never actually get to infinity. And the last one's just negative infinity to infinity, which is the whole thing, which is not really unbound. It is unbounded. It just doesn't have one endpoint. It's all real numbers. Questions on this here? All right. So the first thing we want to do is write each interval in interval notation. We're going to write the inequalities and intervals in interval notation. Interval notation is our brackets and parentheses with our comma, our endpoints. We will not have variables in interval notation. So negative 2 is less than or equal to x is less than or equal to 3. One thing that can be helpful, especially with writing interval notation or inequalities, is we can actually graph it. This year is not asking us to, but if we see the picture, it can sometimes help us. If you don't need to graph it, if you can go straight to interval notation from the inequality, do that. So here, if we did graph it, we have two main points. Our two main points are negative 2 and 3, yes? Negative 2 would go on the left, 3 would go on the right. There are some math teachers and some that want you to have 0, where 0 would be located and then kind of scale it out appropriately, so on and so forth. I'm not going to ask that. I want our main endpoints. Our main endpoints are negative 2 and 3. The only main thing is that they have to be in the right order. Negative 2 is to the left, 3 is to the right. Smaller's on the left, bigger's on the right. At negative 2, We have a point, we have a circle. Is it opened or closed? So is it equal to or not equal to it? -2. Almost. Because -2 is less than or equal to. Since it is equal to, it would be included. Because if we don't have that equal to sign, that bottom line, then yes, it would indeed be open. But since we do have that less than or equal to, we have that line underneath it, we include it. Like if we look at B, x is greater than -1, because it doesn't have that equal to line on it, then it would indeed be open. Make sense? How about 3? Is it going to be opened or closed? It would be. Do we have an equal line or not? It would be closed, yes, because we do have the equal line. So we fill it in. Now we got to figure out where we shade. X is in the middle, yes? So we shade in the middle. When X is in the middle of the two numbers, we shade in the middle. Now for our interval notation, we do have two endpoints, -2 and 3. So those are our two ends, the two bounds of it. Now we just need our brackets and parentheses. Bracket if it's included, parentheses if it's not. Bracket if it's filled in, parentheses if we left it open. So -2 was included, so we put a bracket. How about the 3? Bracket. That's it. So really this is the only answer that this question was really looking for. We did the graph to help us visualize and see it, but we don't necessarily need it. And A was a bounded interval. B, x is greater than -1. Would that be bounded or unbounded? That'd be unbounded because we only have one endpoint. So it's going to go in one direction or the other. Because if we drew it on a number line, the only spot we have is -1. So it's either going to go to the left or to the right. Which way are we going to shade, to the left or to the right? Is x bigger than -1 or less than it? Bigger, isn't it? So which directions are the numbers bigger than -1? To the right. So we would shade to the right. Would the -1 circle be filled in or left open? Left open because it's not equal to it. Now let's look at our interval. So the one endpoint we have is -1, which means we're either going to infinity or -infinity. Which infinity are we going to? Positive or negative? Positive. Since we are going to positive infinity, we would put it on the right. As we said at this point, -1 was not included. We left the circle open, so it has to be a parenthesis. Do we put a parenthesis or bracket next to the infinity? Parentheses. Because no matter how hard we try, we can never get to infinity. No matter what we set infinity at, there is always going to be an infinity that is bigger than that infinity. Seems like an odd concept. I will give an example here in a bit that it actually shows that. Let's look at the next one. -3 to 4. So we have two endpoints. It is bounded. So if we're looking at our interval, one of the two numbers is going to be -3, the other is going to be 4, yes? So we can either at this point have two brackets, one bracket, one parenthesis, one parenthesis, one bracket, or two parentheses. the sign next to -3, would it be a parentheses or a bracket? Bracket, because it's included. How about the 4? Parentheses. And that's it. Now, one of the big things, I do see it every now and then, that y'all want to try to put an X in a interval notation. There is no X in interval notation. We don't put a variable in interval notation. We do put it in with our inequalities, because we're saying that the variable X, or whatever our number X is, that value that we can have with a interval, that X has to be between -3 and 4. This is a compound statement, so we put X in the middle and the arrows would go the same direction. -3 is less than X is less than 4. And since -3 is included, we would say less than or equal to as the inequality equation. Everything sounding good so far? Let's look at the last one. Here, this is an unbounded. We have one endpoint and it goes off in one direction, yes? And our one endpoint is 3, yes? Now, are we going to positive infinity or negative infinity? Negative infinity. Yes. Do we put the negative infinity to the left or the right of the 3? The left, because smaller numbers on the left, bigger numbers on the right. The 3 is included, so it would be a bracket. Negative infinity is not, so we would put a parenthesis. We feel good with this here? All right. So, before we talk about set builder notation, I have a mind kind of puzzle for you. I don't know if they've talked about this before or they mentioned it over in Germany or not. Have you heard of the infinite hotel? So, the infinite hotel or infinity hotel is something to help us kind of at least mentally wrap our head around how big infinity can be. So, the infinite hotel talks about this here. We have a hotel. We'll call it the infinity hotel, the infinite hotel. And we call it that because the hotel has an infinite number of rooms. I will be the clerk running the desk today, trying to help everybody at the hotel. All the rooms are full. We do not have a single room open at the infinite hotel. But a customer comes in asking for a room for the night. Me, being the generous person that I am, I want to try to accommodate and get him a room. So after thinking about it a while, come up with an idea. I asked the person in room 1 to move to room 2. Person in room 2 moves to room 3. Person in room 3 to 4, 4 to 5, 5 to 6, 6 to 7. We do have an infinite number of numbers, yes? So everybody else has moved down one room, which means that room number 1 is now open. So the new person can move into room 1. We had an infinite number of rooms, yes? I just now made it one bigger. We now just made an infinity bigger than what we started with, yes? So even if we had managed to make it to the first infinity on our number line or set, we just hit one bigger. We didn't reach it. There's another one. Make sense? The CEO of the Infinite Hotel, it's become so popular, he decided to actually expand across the road and open up a second Infinite Hotel. Business is booming, both hotels fully packed. Unfortunate event happens and Hotel B burns down. There's no more. But luckily, everybody in Infinite Hotel B made it out just fine. However, they need a place to stay for the night. So after thinking about it for a while, we figured out a way to get all the people in Infinite Hotel B, all those infinite rooms, into the first Infinite Hotel, even though the first one's rooms were all booked up. And what I decided to do is I'm going to take the person in room 1 and move them to 2. This seems very similar to what we just did, isn't it? But I tell the person in room 2 not to move to room 3, but to go to room 4. The person in room 3 is going to go to room 6. The person in room 4 is going to go to room 8. The person in room 5 is going to room 10. We're moving them all to the next even number. How many even numbers do we have? Infinite number, yes? How many odd numbers do we have? Infinite number. We now just opened up enough room so that everybody in the infinite hotel B can actually move into the infinite hotel A. Essentially, we just doubled infinity. Kind of crazy, isn't it? And again, you could do this up to 7 infinite hotels and merge them into one. The math gets a little more tricky as we go up, but it is possible. And the reason I say that or talk about that is just to get us to be able to wrap our head around the fact that infinite is such a concept. There are some infinities that are bigger than others. To quote, what is it? Fault in Our Stars? Because they do say that in there. But next thing we're talking about set builder notation. Set builder notation is nice for us to be able to describe a group of numbers that we can't actually write out or have a set pattern for. That's where this is helpful. That's where this is convenient. We use symbol to define a set in terms of the properties of the members of the set. Now, the first thing we're looking at is the triangle. What goes in place of here is the type of numbers we're talking about. For the most part, we're going to talk about the set of all real numbers. If we're talking about the set of all real numbers, we're just putting x in place of the triangle. So it could be x is an element of the integers, x is an element of the real numbers, x is an element of the natural numbers. We're telling what type of group of numbers are we talking about. The line in the middle stands for such that. That's literally all it is. That bar means such that. And our circle is the description telling us more information about the numbers. Is our description. I've started using this here, these 3 symbols, so that we understand that different pieces go in here. The only thing that stays the same is the bar. Okay? So normally, we can write this example below it. For the most part, if we're talking about the real number system, we're going to have brace x bar. I've said it before, I will say it again. Mathematicians have a tendency to be lazy. Because really, I wrote a brace, I wrote an x, and I wrote a bar. 3 things, yes? What that stands for, and as we read it, that brace x bar stands for the set of all real numbers x, the set of all real numbers x, such that. We condensed 9 words into 3 symbols. That's a shortcut, yes? That there, these 3 symbols is a set of all real numbers x, such that. Then we put a description in. X is greater than 3. So we're saying that for this here, the set that we're talking about is the set of all real numbers x, such that x is greater than 3. So we've defined every number bigger than 3 with this here. Which before, if we tried to write this out, we'd had to do a brace. 3, well, we wouldn't include 3 because we just said bigger, so 4 would be the first one, yes? Actually, it wouldn't. Because we said specifically all real numbers were actually greater than 3, yes? 3.1. Would that be included? How about 3.11? 3.10254? 3.8967212? There's a whole bunch of numbers between 3 and 4, yes? And according to this, we would have to list every single one. There is no way to do that because the set of numbers between 3 and 4 is also infinite. You can fit as many numbers between 3 and 4 as you want. You're doubting me on that. A little bit? 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6. I can do 1 over every number. Infinite number of numbers, yes? Then we can say, because we won't say, because we could not going to say 2 over 1, so 2 over 3. 2 over 4, which would reduce to a half. 2 over 5. We can fit all those, yes? 3 over 3, 3 over 4, 3 over 5. Some of these, I know these are false, but there are ways to do it fractionally, because this here is actually between 1 and 0 and 1, not 0, 3 and 4. But between any two numbers, we can do these fractions and get them all to fit. Does that kind of make sense? I mean, you don't have to fully know it, but it is possible to fit an infinite number of numbers between two. In the last few days, I've taken us, we're going to see how abstract this can be. But what we're going to do is look at this here and kind of see what we're talking about with set builder notation. It gives us a way to describe numbers, types of numbers. So when we look at the first one, brace x bar, the set of all real numbers x such that x is less than a. Okay, you ready to graph this? So we're saying whatever x is, its values have to be less than a, yes? So if we graphed it, well, on that number line, we're going to have the point a, whatever a is. A is going to be a real number. Is it equal to it? No, so that circle would be open, yes? Since x is less than it, we would shade to the left. Graphically, that's all that's saying. It's all the numbers less than a, whatever a is. Why does it feel like it should be more than that? Doesn't it, a little bit? But that's it. That's all it's saying. The second one's kind of a little bit easier. Brace x bar, the set of all real numbers x such that x is what? Not equal to 3, yes? So we do have 1 point on this here, and it is 3. Would we fill that circle in? No, right? Because it says what? X is not equal to 3, yes? So what could x be? Not 3, so what could it be? Anything. It could be what? 4, pi, 9. Any number as long as it's not 3. So it could be all these numbers here. Or all the numbers on the other side. It cannot be 3. That's kind of nice, isn't it? Pretty much everything but 3. Don't know what 3 did, but it's excluded. The next one, the set of all real numbers x such that negative 4 is less than x is less than or equal to 6. So notice that we have all the real numbers such that negative 4 is less than x is less than or equal to 6. So if we graphed it, we'd have the 2 points, negative 4 and 6. Negative 4 would be open, negative 6 would be closed. And then we would shade in the middle. Because x is in the middle, we shade in the middle. Because that's all it's saying. It's saying the set of all real numbers x such that negative 4 is less than x is less than or equal to 6. It gives us a way to describe this without having to A, list all the numbers between negative 4 and 6. Too many to list. And it gives us a way to visualize it also. Now, I will show you this here, this next one, that E is element. X is an element of, we can fill in a number type. Because there are going to be times where we're not specifically talking about the real number system. we want to say that x is an element of the integers. So we can fill that integer in. So instead of saying that x is the set of all real numbers x, we're saying the set of all x's in the integers. All the x's are elements of the integers, such that x is greater than or equal to -9. This one here is not fun to graph. So less than or equal to, we'd have -9 and we'd fill it in, yes? And we said that x is bigger than it. So it's very tempting. We want to shade to the right, yes? Well, what's the next integer after, bigger than -9? Be -8, yes? Can we have any number between -9 and -8? Because we can, -8.5. Is that an integer? No, that's a rational number, yes? So none of the numbers between -8 and -9 are integers. So we'd have -8. And then we'd have -7. And I'm going to stop there because I think you're noticing how tedious this is, how essentially we would have to make a point at every integer going to the right. That's not practical to do and do it by hand because we'd have to do one for -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. And that's also why I'm not going to graph the last one. X, for all real numbers x, such that x is even, we'd literally have to have all the points. We'd have to exclude every odd number. But we kind of get and see this here, yes? Graph each of these here in set, each of these that are written in set builder notation. Really just says graph the inequality, graph the equation, graph the statement. So our first one says that for all real numbers x, such that x, or 2 is less than x is less than or equal to 5. So we're really just graphing the inequality 2 is less than x is less than or equal to 5. So we have two main points, one at 2 and one at 5. Yes? Our 2 would be open and 5 would be closed. And because x is in the middle, we shade in the middle. That's it. Questions on A before we look at B? B, we have an or statement. Or statements mean that one or both can work. Because it says the set of all real numbers x such that x is less than or equal to 0 or x is greater than 4. So we do have 2 points. Or statements we can go on and throw on the number line. Or statements means one or the other must be true, or both. It is possible for both statements to be true. At 0, would we fill this circle in or leave it open? We would fill it in. The 4, we're going to leave it open. For x is less than or equal to 0, would we shade to the right or to the left? Left. X is greater than 4, would we shade it to the right or to the left? That's it. Or statements, it is possible to have the 2 statements head at each other, and that would end up covering up the whole number line. Because if we said that x was greater than or equal to 0, and x is less than 4, if we flipped it, you don't have to write this down. For 0, we would now shade to the right. For the 4, we would now shade to the left. We end up covering up the whole number line. And I had the question, I showed this earlier today, would we still include the 4? And let's put it in to the statements. Because here is 4 less than 4. Is this true? Is 4 less than 4? No, it's equal to it. So this is false, yes? Let's look at the other one. Is 4 greater than or equal to 0? Is that a true statement? Is 4 bigger than 0? So is 4 greater than or equal to 0? Yes, isn't it? So this is a true statement. With or, 1 has to be true. So even though 4 does not satisfy the x is less than 4, but since it does satisfy our x is greater than or equal to 0, it works. It is included. Because or, one of them has to be true. But let's look at the next one here. Last one we'll look at today. Sketch the graph of the set of numbers for all real numbers x such that x is less than -2 or x is greater than 0. So again, we do have 2 points. -2 and 0. Is either one of these filled in? No, they're both open. For -2, do we shade to the right or to the left? Left. 0, do we shade to the right or to the left? Right. That's it. Questions on this here? I think we feel comfortable with these here, yes? So tomorrow, first thing we're going to start off with is writing what they give us in set builder notation.